It is well known in mathematical circles that relatively few of all the real numbers can be written in finite decimal form. That is, even though there is an infinity of numbers, each of which can be represented by a finite collection of digits, there are many more numbers, like 1/3, square root of 2, pi, and so on, that cannot be written in this way. Stibitz and Jules from Mathematics and Computers. Digital computers are really propped up by a series of tricks and deceptions. Now, I don't mean that in any dramatic or sinister sense. Rather, the digital approach has all of these technical issues. On paper, it's very flawed. You have to represent numbers using discrete elements. That means something as simple as 1/3 or pi can never be accurately represented. A computer's supposed to do math, and pi is pretty important to mathematics. So that means digital is a non-starter, right? If we're going purely by theory, then an analog computer is strictly better than a digital. Analog machines can represent any real number with any degree of accuracy. So that makes it the winner. And obviously, we all live in the analog world every single day. But theory and practice are worlds apart. When the rubber meets the road, or rather, when the digits meet the circuits, theory goes out the window. Early digital machines just can't keep up with analog, but that quickly changes. As it would happen, the digital branch of the family has this wonderful ability to grow and expand. Case in point, how many of you have really thought about digital approximations of numbers in your day-to-day life in the last decade? I'd wager maybe a handful of you. Approximation has gotten better and better to the point where we don't even notice the issue anymore. At least, not in places where it actually matters. In theory, however, analog should just be better. But that branch hit a roadblock. Once analog machines approached their limits, well, all bets were off. That's when we start to see some truly radical designs coming out of the woodwork. Welcome back to Advent of Computing. I'm your host, Sean Haas, and this is episode 173, Hybrid Programming. Today is a surprise continuation of last episode. If you can remember back a few weeks, we were discussing analog hybrid computers. Those were systems made up of a digital computer connected to an electronic analog computer. I cut things off right as I was getting into a particularly interesting topic. That is, how do you even program these things? You had options. On the one hand, companies like EAI offered special Fortran libraries that let you interface with the analog part of your hybrid system. That has the massive upside of being Fortran. Anyone who knew Fortran could get up to speed pretty quickly. On the other hand, there are new languages designed specifically for hybrid computers. Or at least, that's how things appear. These are programming languages that are used on a digital computer, but somehow do a bit of analog work. That's something I could have never even imagined before, well, a few weeks ago. I always say that there's a wild depth to the history of computing, and this is the perfect example. In this episode, we'll be examining these mysterious languages. Specifically, I want to look at two languages, Apache and Hytran. We'll be looking at why special purpose languages were developed for hybrid systems. I also want to understand just how different these languages are from a more normal digital programming language. In general, though, I just want to know more. What in the world does it even mean to be a hybrid programming language? As we begin, I think it would be a good idea to outline the problem at hand. A hybrid computer is composed of two parts, a digital side and an analog side. Those sides communicate over an analog to digital link. Programming that digital side is simple, or at least it's something we can recognize as programming. You can use any language that computer supports, from machine code up to a more sophisticated tongue like Fortran. What's crucial to recognize here is the digital computer is executing a series of steps encoded as numeric instructions. Move this number over there, add that number, and so on. Analog computers just do not work that way. An analog machine operates continuously on continuous values. It doesn't process a series of commands. Rather, it's composed of discrete components that an operator wires together to create a quote-unquote program. That program is entered using physical wires hooked into a plug board. It's a manual process that doesn't involve any automation. The other crucial point here is the level of interactivity. Hybrid languages appear in the 1960s. At that point, most digital computers were non-interactive. Programs were executed in batches, and a programmer would only ever interact with a computer very indirectly. Analog machines were almost the exact opposite in this regard. They were, by design, interactive. A user would physically work the machine, making adjustments and watching outputs change in real time. There's a much more touchy-feely kind of aspect to these types of computers. There lies the heart of the issue. Analog and digital machines are very, very different types of computers that are operated in very different ways. That's why the concept of a programming language for a hybrid computer seems so wild to me. How can you program a computer when half of the machine uses a plug board and half of the machine is non-interactive? It almost seems like the gulf you'd have to span is simply too wide. Hopefully, you're seeing just what a huge task this really is. The problem fell more on the analog side of the equation. I mean, it kind of had to, right? We're talking about a stored program, as in a program that's stored in memory as a series of steps. That's a pretty inherently digital thing, at least as we conceive of it. That made the analog component the oddly shaped puzzle piece, so that's where work was being done. The programmability of analog machines was a known issue since way back. A neat source about the issue comes to us from a 1967 contract between NASA and Electronic Associates Incorporated, or EAI. That report, Stored Program Concept for Analog Computers, is a bit of a wild document. It opens with a pretty funny problem statement. Quote, "Eliminating the patch panel has long been the dream of analog computer users for a number of reasons. One of these is psychological. The sight of a large mass of wires hanging from the front of a computer is ugly and disturbing to almost anyone except a true dyed-in-the-wool analog man. And even some members of this select group are more than willing to see the patch panel give way to a deck of cards or a punched tape. These aesthetic considerations alone are enough to discourage many novices and cause them to turn to a digital computer with a simulation language." End quote. The digital lab gets sleek machines, so why can't we? On a more serious note, there are some core issues with the classic patch panel. The report outlines 3 of those, outside of the mess, of course. Those are ease of programming, stored program capability, and reliability. These may sound like pretty generic issues, but there is a bit of subtlety here. The paper was published in 1968 off the back of a 1967 contract, but it cites back to an earlier 1961 study. So there is some history here and some context around these 3 main issues. Some earlier works I've read, notably Corn & Corn's fabulous electronic analog computers, point to the fact that analog computers were actually easier to use than their digital cousins. Their reasoning came down to access and interactivity. I think that makes sense, right? An engineer could plug up an analog computer without calling in a mathematician or the mysterious and newfangled programmer. And that could all be done alone, with instant feedback and physical access to a personal computer. But by the latter part of the 1960s, things had started to change. There are now tools, notably languages like Fortran, that make it possible for an engineer or researcher to program a digital computer without the aid of a mathematician or, yet again, a newfangled and mysterious programmer. In that context, yeah, programming could be easier than working a plugboard. I also have a bit of a theory that I can't back up with the sources, but I can with, my thoughts and feelings. I think it's probable that by the 1960s, there were more programmers in the world than there were plugboard operators. I don't know if I could even find the data to prove that. We know there was a meteoric rise in the adoption of digital computers, and that outpaced the production of analog machines. That would have had an effect on the population of experienced plugboarders. Specifically, it would have led to something that I like to call ecosystem death. At least, that's what I call it when I talk to other programmers out in public, usually at bars. I've seen this firsthand. I was a professional Perl programmer back in the 2010s. That was kind of around the end of the language's heyday, or at least it felt kind of like the end. I got to watch in real time as there were just fewer and fewer of us. The packages I was using were actively being deprecated. I remember having to use older versions of a database and tooling for it because there were no longer Perl libraries that supported the newer version I would have preferred to use. There were also just fewer and fewer Perl hackers. Years later, I ran into a man that ran a team that worked with Perl, and he talked my ear off for hours about how hard it was to find new Perl programmers. Resources, knowledge, and human power were just eroding away. I've been more recently seeing a similar trend with PHP development. That language is also kind of evaporating. There are fewer and fewer PHP programmers, and a lot of PHP packages are becoming deprecated or not working with newer versions of external software. Analog computing would have faced a similar ecosystem death in this period. Fewer folks used analog machines. Fewer new tools were getting created. I get the feeling there was just less energy for pure analog. It was moving from mainstream to niche. In that context, ease of programming takes on a whole other light. There were just more people who knew how to program a digital computer than could ever put together a plugboard. The stored program capability point is equally interesting and very pragmatic. Due to a few very fancy words, stored programs are actually much better than non-stored programs. If you have a stored program in some kind of memory, and you can inspect and modify that memory, you can do all kinds of fancy things. That includes everything from self-modification to much nicer operations like compilation. On the more practical side, we have very real-world issues with plugboards. Technically, an analog program is entered on what's called a patch panel or patch frame. These can be removed, worked on at a desk, and then hooked back into the computer. The panels themselves are pretty simple. I have one from a tabulator hanging above my desk that I'm looking at right now. It's a metal frame with a handle on one side. Its face, where you plug in patch cables, is a non-conductive sheet of material with a grid of holes. I think mine's made from Bakelite. There's also printing on the face of that sheet to tell you which holes do what. That gets mounted on the machine over a grid of contacts. Patch cables that were hooked into that panel get pushed onto those contacts. It's a nice setup that, in practice, lets users physically store programs. You could work up a nice damped oscillation simulation that you liked, take the patch panel, and then store it away for later use. There were even special cabinets made for storing these panels. The downside is that takes up a lot of space and it costs a lot of money. If you want to store a new program, you have to have a spare panel around and spare space. That actually puts a practical limit on how many programs you can store, which is a funny thing to consider, right? Then we get to reliability. In the EAI report, this is a matter of, again, practicality. Patch panels are physical and can get messed up in transit. The example used is literally cables getting unplugged while moving between the computer and one of those storage shelves. There's also an unstated side to this, that is, reliability of setup. A program will do the same thing every time it's executed, at least in theory, if it's working correctly and all that. But a patch panel has to be manually constructed. If you handed the same circuit diagram to two patchers, you would probably get two different panels. That's workable, but not exactly reliable. So, what's the solution? Well, as it turns out, that's not entirely clear. The EAI report lands on one possible fix, but not necessarily one that's all that practical. It recommends the use of a series of switching matrices. The report actually draws inspiration from Bell Telephone's phone switching systems. Basically, we're looking at a very sophisticated switching setup that routes analog signals inside a computer in a similar way to how Bell was routing analog phone calls in this period. Physically, this means you could tell the machine to connect the output from one component to the input of another. The computer would then jostle contacts and relays until the connection was made. The actual signal would end up traveling through a few matrix switches and eventually find its target. That's workable, but it ends up being very, very complex to implement. The report estimates something like 20,000 switches will be needed to create a fully programmable EAI 680. Just for comparison, UNIVAC 1 used 6,000 vacuum tubes. That's 6,000 switches. But to be fair, that's an older design. By the mid-60s, you could get a PDP-8, which used 1,400 transistors. So a programmable analog computer would be significantly more complex than a digital machine. That's a bit of a problem. With that being the case, you better have a very, very specific use case for why you need this supremely complex analog computer. It does, however, get worse. The situation continues to deteriorate. Remember some of the upsides of analog computers? Well, you got flexibility and interactivity. Those are the secret weapons here. But here's the thing. A programming system can upset that. From the EAI report, quote, any automatic patching system will have to restrict the flexibility of the analog components to some extent. As a minimum, the analog programmer will have to give up his summing junctions, ungrounded pots, and various configurations of loose resistors, diodes, and capacitors hanging from the patch panel. At this prospect, many people will say, good riddance. Of course, the programmer should still be allowed to do what he wants to do, but he will be restricted in how he does it. He will have to express what he wants to do mathematically rather than saying, I'll just stick a diode here. End quote. It was regular practice to patch in components and to do all kinds of fancy hacks to get a circuit to work. This, to me, sounds very similar to what older programmers would do with machine code, where you'd be able to do much fancier things than any language could ever allow. It was also practice to move things around in real time. A switching system would make both of those practices, hackery and interactivity, nearly impossible. That is a pretty big hit for the analog camp. It's sounding more and more like we just end up with a more complex and less accurate computer. That's the bad and the weird, but what about the good? What's the benefit here? The EAI report proposes two programming languages. Really, it's two levels of one language, and I've seen this in some similar analyses of analog programming. One is an abstract analog program, and the other is a concrete program. That's pretty unclear, right? The abstract program would be the equivalent to something like a wiring diagram. It describes what kind of components you want to connect up. You need an integrator here that's hooked to the output of a summer, a potentiometer with its output hooked to the other side of the summer. It describes the circuit, but in general terms. The concrete program describes the actual connections. Wire output 1 of integrator 12 to input 1 of summer 5, and so on. That concrete program is used to control the switching matrix, and would be generated from the abstract program. This may sound like a more familiar technology. This almost sounds like assembly language and machine code. However, there's a key difference that should prevent comparison. One abstract program can be turned into many different possible concrete programs. A machine like the EAI 680 has dozens of summers and integrators. Our abstract code could be solved by wiring up any two in combination. In an assembly language, a line of code gets converted directly into an equivalent machine code instruction. There's no room for ambiguity or multiple solutions. I point this out because even as we're trying to make analog machines behave more like their digital cousins, there are some very fundamental differences at play. The EAI report gives us a pretty good rundown of the challenges with programming an analog computer. But it's pure theory. What happens when we actually try to program a hybrid machine? Do these same challenges carry over? And is there actually an automatic solution here? My timeline here may not seem entirely chronological, but I assure you there's some logic. That EAI report is working, in part, off an earlier report from 1961. So I've been kind of viewing that as an update to some earlier paper that I can't actually find scans of. But it means that the problems were still apparent in 61. So when I introduce our next source, and that source is from 1963, just go along with it. I'm building a timeline. I swear, things are in order. Around 1963, Euratom, the European Atomic Energy Community, develops a language called Apache. This work is specifically coming out of a research center in Ispra, Italy. See the initial issue here? Some of the sourcing on Apache isn't in English. This, apparently, was enough of an annoyance that period publications even point that out. I bring this up because, really, I want an excuse for relying on unsatisfying sources, or at least an explanation. I'm working off an English language paper about Apache that's published in the journal Mathematics and Computers in Simulation, and some manuals for the language. I haven't been able to find really much information on the language's creators, or anything like a nice interview or oral history, so we're on the technical side today. Buckle up. Apache is a programming language developed specifically for analog computers. Where this gets a little ambiguous is the hybrid component. Strictly speaking, Apache is for programming analog only. You have to use another program to deal with hybrid interfacing and all the digital side. In practice, that means Apache would probably end up being one tool in a larger hybrid tool chain. What Apache lets you do is write a program in a digital computer and compile it into a list of connections for an analog patch board. I should set expectations here. This is not fully automated. Quote, "At present, there exists no switching system capable of realizing the circuit connections automatically. With Apache 2, we can obtain, however, the commands corresponding to such a system, punched out in a coded form. A semi-automatic apparatus is visualized as the first step towards full automation." End quote. That's neat. Apache is partly aspirational. It's hoped that eventually we'll have automatic patching systems, but right now, we don't. So you get instructions for patching that could be fed into a theoretical patching machine. But in 1963, those instructions still have to be fed to someone with a pocket protector. Immediately, that's pretty unique. It's not all that often I run into a language whose target platform doesn't really exist. Apache is straight up a language designed for the future. I think that's cool. That said, we have to get to the brass tacks. What exactly was Apache like? Well, it's very similar to Fortran with quirks. Apache is meant to be used to model equations. No surprise, right? You express an equation using text, and then Apache will convert that equation into a circuit. There are also classic digital things like loops and conditionals. Apache supports a do loop, which is very similar to early Fortran loops. And it has two statements, switch and condition, that basically work like an if statement in a more mundane language. It's the purely analog features that make Apache strange. What's wild is that Apache actually does look like Fortran if you just skim the code. It has very similar syntax. But if you actually start reading, well, maybe don't do that. That's where things get weird. Let me start with what I think is the most apparent difference, the concept of a scale factor. An analog machine uses some internal voltage range to represent a variable, but presents a numeric value that's been scaled, or rather, the programmer does scaling so that you get a proper numeric value. Apache is developed for the EAI PACE 231R, one of our favorite machines from last episode. That's a 100-volt computer, meaning values are stored as a voltage range between minus 100 and 100 volts. If you're dealing with a number that ranges between minus 100 and 100, things are easy, right? You can just read out the voltage directly. But what if you want to model a variable that ranges from 0 to 10? Then you have to scale. Normally, a human would work out that scale for each variable, and you'd wire everything up accordingly. But Apache does that for you, automatically taking scale into account. How is that represented in code? Well, it's a two-step process. First, you have to set a reference voltage for the entire program. If you don't have a reference statement, then the reference is assumed to be 100. We are an EAI shop here after all. That part isn't too off, it's just a setting for the program. Lots of languages, including Fortran, have a similar concept. This becomes more intrusive when you define a variable. In Apache, variable definitions require 3 values: initial value, minimum value, and max value. So you'll see lines like x equals 7, 0, 10. That would mean that x is a value that ranges from 0 to 10, and it starts out as 7. That's a little weird. In my digitally addled mind, this is a static check kind of thing, right? When I first saw that syntax, it immediately made me think of Ada's precision typing. In that system, you can set value ranges for variables, and the program won't compile if you do something that violates those boundaries. But that's not really the case here. Apache isn't a procedural language, it's a tool for defining circuits. You can't define X in one spot and then change its value in another. That's not an applicable concept. Instead, defining a variable is part of setting up a circuit definition. What makes this more mind-bending is that the initial value part is optional. It's actually the only part of a variable definition that is optional. You can just say that X is a number between 1 and 10. That's perfectly valid code. Why would you do this? Well, in many cases, X is a placeholder. It's the output point for some equation that gets defined later. Equation definition follows this same pattern. They look like Fortran, but on closer inspection, they're not Fortran. Normally, an equation in a program is actually a declaration. You're saying that you want to set the value of some variable to the value of some expression. X equals 1 plus 1, or X equals function of Y, that kind of thing. This is usually broken into two sides along the equal sign, the left-hand side and the right-hand side. In the expression x equals 1 plus 1, the left-hand side is x, the right-hand side is 1 plus 1. The rule, almost universally, is that the variable on the left-hand side is set to the value of the expression on the right-hand side. I realize I'm being heavy-handed here. But please laugh because that's a good joke. And also, please accept my heavy-handedness for a few more minutes. The point is, these things follow a pattern. Crucially, that pattern isn't the same as in formal mathematics. On paper, it's valid to have expressions on both sides of the equals sign. You can even say something like 1 plus 1 equals x. That's perfectly valid. But Fortran would not compile it. But that's kind of a digital restriction, it turns out. In the digital world, a program revolves around setting discrete values in discrete locations in memory. But over in analog land, there's no such restriction. You can model just about any equation as a circuit. That doesn't come with the left-hand, right-hand restrictions of a digital programming language. The first example of this oddity I ran into was the derivative. Apache supports modeling derivatives natively. It does so using kind of weird syntax. The nth derivative of some equation is written as der n of x. That x is in parentheses as an argument to a function. So the first derivative of x would be der1 of x. That's kind of strange, but whatever. Apache doesn't really do multi-argument functions for some reason. The big weird is how you actually use derivatives. Apache allows you to have an expression on the left-hand side of the equation if that expression is a variable times an operator. Derivatives count as operators, and so do a few other things. In more basic terms, that means in some cases, you can have expressions on the left-hand and right-hand side of an equals. For a derivative, that would read something like a times first derivative of x equals blah, where blah is some kind of differential equation. This is strange to see, but really neat to consider. It means you can directly translate a differential equation as written on paper into Apache. You just have to deal with converting notation, which any mathematician will know how to do. That's a huge upgrade compared to, say, Fortran. In a digital language, you have to do the whole approximation dance. That means, in practice, you have to write a bunch of code. You can't just say, differentiate this equation and call it a day. But Apache lets you do that. The result of all this equation magic is a concrete program. Just like the earlier EAI report, we have a note to drop in here. Quote, it is possible to write a problem using a large variety of equation types, thus allowing a form which is very near to the physical problem to be chosen. After treatment by the machine, the equations are rewritten in a normalized form corresponding to one and only one analog circuit. End quote. A single equation can be represented with a number of different possible circuits. Apache chooses one of those options as it compiles your code. You end up with a single concrete program. I bring this up again because this is so different than a digital targeted compiler. Digital computers can do some ambiguity, but not in nearly the same way as an analog machine. Apache also handles setting constants. These are called parameters, values that get fed into the machine and don't change. The PACE 231R had these things called servo potentiometers, or servo pots. This is basically what it sounds like. A potentiometer is a variable resistor. It's a dial you can twist, and as you twist it, the resistance changes. Many volume knobs on old stereos are actually just potentiometers. The servo potentiometer is a servo motor that's physically connected to the shaft of a potentiometer. That gives you a way to automatically set a resistance, or a constant value. With its wiring list, Apache would also output a list of constants, which could be used to automatically set those servos. That list was actually punched and could be fed into this wild thing called the EAI ADIOS, the Automatic Digital Input-Output System. It's a hokey name, and I'm kind of surprised I haven't seen anyone else use ADIOS as an acronym. Anyway, the ADIOS would look immediately familiar to any digital nerd. It's a desk with a teletype and a tape reader. It lets you automatically enter values into your analog computer. Specifically, it was meant to set those servo values. Apache is really making aggressive use of every feature of the 231R, including all these modules and external devices. Those are all the neat features, and here's the cursed stuff. Apache has a number of features that are very, very analog specific. One is the omit statement. Conceptually, Apache treats each plug on a board as an address. Omit lets you tell Apache to never use certain plugs. You just say which address you want to omit, and Apache tries to solve for a circuit without using those addresses. This is useful if your analog computer has some broken or missing components, or if you're trying to share a plug board between multiple projects. I can't even think of a digital equivalent to this. It sounds like some intercal joke, right? Please do not use this memory address. But it gets stranger. Check this out. To quote from the Apache paper I've been using, suppress followed by a statement number. This is in order to efface the relevant statement. It is often followed by insert. This is followed by the number of a statement before which it is wished to insert a new statement. End quote. Remember how I said Apache isn't really procedural? Well, that's not 100% true. Every line is numbered, and there are some statements that care about order of execution. Well, let me be careful there. Not exactly execution. It's more like read order for some pre-processing step in the compiler. Remember, nothing is actually executed. It's all just used as input to create a circuit diagram. Suppress and insert let you replace earlier lines of Apache code. Suppress, at least, is 100% an intercal operator. I think the correct word in that language would be forget or abstain. Now, what's up with these keywords? I'm just not entirely sure. I have some later manuals for Apache which contain omit, but not suppress or insert. That sucks because I was hoping to find some example code or further explanation. I think this may just be some weirdness due to the era. Some of these languages in the 60s are just a little off. My only guess is that suppress or insert were meant as a way to improve developer experience. My guess here does take context into account. It would have taken a long time to patch up a board, but compiling an Apache program would be pretty quick. The trade-off here is flexibility and interactivity. You can't just pull a wire out of a program. That doesn't exactly work. But on a patch board, well, you can rip out anything you want while the thing's running. Suppress could serve as an easy way to see what kind of circuit Apache would generate if a given line was removed. Or, put another way, it could give you a way to virtually rip out a cable. Insert could let you patch in a replacement. Now, I don't know if I'm super convinced that this is the reasoning, but I don't have enough information to give a better guess. I got to thinking about this developer experience, or DX aspect here, because Apache does make some seriously heavy considerations to DX. The core of this revolves around patching. Remember how Apache will output commands for an automatic patcher that doesn't exist? Well, Euratom kinda made one. At least, they made a device to help with patching. The device in question was called, I think I'm going to call it Satanas or Satan As. It's the semi-automatic analog setting thing. Satan As ate the auto-patching cards that Apache created, and it used that information to tell the programmer what to do. That's not really a simplification. That's the whole bit. Satan As was a big frame that a patch panel could be mounted on. Under the frame was a grid of lights that aligned with the holes of the patch panel. The entire apparatus was wired up to a punch card reader. An operator could feed in Apache's output cards, and then Satan As would light up where wires needed to be placed. Was this done one connection at a time? Was there some way to tell Satan As to move on to the next connection? Was it useful? I wish I could tell you. That's about all the information I have on Satan As. I wish I could find a photo of this thing. In theory, the device solves one of the key issues with analog computers, that is, reliability of patching. It improves the developer experience greatly by telling them what to do next. By following the lights, you could end up with the same patch panel every time. I don't think anyone at Euratom was thinking about DX, but Satan As really feels like it fills a similar role to some digital programming tools. It's automating away some of the error-prone handwork that programmers are forced to do. Now, it's still not quite there yet. The technology was just plain missing. Put together, Apache is a surprisingly aggressive tool. It's aiming to solve many of the issues that faced analog computers as the digital revolution caught up. It gave a certain ease of programming, increased development speed, and it makes programs more reliable. But that comes at a heavy cost. Apache is kind of janky. Analog technology just wasn't quite ready for what the authors of Apache wanted. And that's an interesting mismatch. It kind of refutes my earlier vibe check, doesn't it? The authors of Apache are clearly looking to the future. They have a number of features like auto-patching that are developed explicitly for some future analog machine. It only makes sense to add that kind of feature if you believe analog has a future. So maybe I'm wrong. At least a group of programmers in Italy seem to think so. But Apache, despite its aggressive forward-looking nature, is still only a partial solution. It's a way to use a digital computer to help program an analog machine. That's useful for hybrids, but it's no one-stop shop. This gets us to the topic that made me diverge into this episode, Hytran. This is EAI's first-party hybrid programming tool, but to be blunt, it's not a very straightforward product offering. It's taken me a bit to understand exactly what Hytran even is. The reason for that confusion is that Hytran had a bit of an ecosystem develop around itself. Hytran isn't just a programming language, it's also a set of analog development tools, an interactive interface, and a simulation language. It's kind of a pile of things, so it's annoying to tell exactly what a paper means when it just says, oh, we used Hytran. EAI themselves initially describes the thing like this, quote, Hytran, hybrid translator, will be used to refer to a family of metaprograms being implemented for the HYDAC 2400, end quote. You may laugh, but it even took me a while to find out what Hytran was short for. So, do you notice the strange word here? What exactly is meant by a metaprogram? Well, we are kind of off the beaten path here. In the digital world, we have these things called metaprogramming languages. These are languages used to describe the syntax and structure of another programming language. One example is Bacchus-Naur form, which is initially used to describe the syntax of ALGOL. The whole point of a metaprogramming language is to give us a way to talk about a language in exacting detail. But I don't think the term metaprogram here means metaprogramming language. At least, not exactly. I think this is a quirk of some of the weird language around analog machines. Remember, on the fringes today. Some sources refer to a completed patch panel as a program, and the act of completing that patch panel as programming. EAI's documentation, notably, uses that convention. My educated guess here is that metaprogram means a program that's used to generate another program. Hytran takes source code on a digital computer and then uses that code to generate instructions for patching up an analog computer. In that sense, using EAI's own terms, it's turning a program into a program. Hence, it's a metaprogram. I don't, however, understand why EAI didn't use the term compiler. We've had that kicking around, well, forever. EAI even had their own Fortran compiler at this point. They even call that program a compiler. I mean, if you really want to be specific, you could call Hytran a transpiler or a source-to-source compiler. But for whatever reason, we get the fancier and more confusing term, metaprogram. Long-winded explanation of the simple fact that Hytran things are a little confusing. But luckily, that confusion worsens with time, so we can start off with the first paper on the language and work up from there. In 1964, a duo of EAI nerds published Hytran, a software system to aid the analog programmer. Note that EAI uses the term programmer here. This version of Hytran is at a point where it's just an analog language like Apache. That said, Hytran offers a different set of features when compared to Apache. This may have been intentional because this paper does cite the earlier work we covered on Apache. To quote, "The input language used in Hytran is oriented towards the analog programming procedure rather than towards the digital machine. Input data can be written in a form which closely resembles the programmer's own way of documenting analog programs." End quote. Apache initially struck me as a tool that lets you work an analog computer almost as if it were digital. It's full of all kinds of discrete goodies that digital denizens would appreciate. Hytran, however, is more explicitly canted towards the analog side. Hytran is primarily a tool to make analog programming easier using a digital computer. You know, like the paper's title. It's a pretty explicit, not reading between any lines here. The key difference between Apache and Hytran is that Hytran can deal in more concrete patch configurations. A programmer can enter exactly how they want to patch a problem. I want to highlight that difference. In Apache, you enter a problem as an equation, then Apache works out how to wire it up. In Hytran, you enter a problem and then enter the component interconnects. You actually pass in the finalized wiring diagram. That, on its own, is a different flow. Apache is pretty well set up to give you the same flow as a digital programmer. You work out what equations you want to model. You write it out, then you let the compiler figure out how to do it. Here, Hytran is really just a tool in the analog man's belt. You work out the equation to model. You work out a wiring diagram, then you enter both into the digital computer. That sounds almost useless. What's the automation? What does Hytran do to help you? If I were to summarize, Hytran's much less digital, but it's much more hybrid. It includes these things called offline and online checks. This is a set of tools that lets you make sure you're using your analog machine correctly. And it does so using the digital side of your computer and the analog digital link. On/offline is a little weird here. In the digital world, offline has historically meant working away from a digital computer, as in using an isolated key punch to enter data for later use. But HiTran is hybrid, so offline means working without the analog computer on. Online means, well, working with that analog to digital link established. In offline mode, HiTran uses a digital simulation to test your analog program. It checks voltages and propagates them down simulated resistors and capacitors. This spits out any egregious errors. But that's really just the starting point. The offline mode, also called a static check, gives a set of expected values. Those are stored for the next step. In online mode, the digital computer supervises the analog computer. It uses the values calculated during simulation to make sure the analog machine is functioning correctly. This will flag errors and issues in real time. That includes things like catching patching errors. HiTran is smart enough to say if you misplaced a cable. That's pretty cool, right? And it's a use case I didn't think we'd run into. In my head, the digital computer is always the heart of things, and the analog machine is just kind of a vestigial organ. HiTran flips that, using the digital machine as a handy tool that makes up for the analog machine's deficiencies. It's clear to me how this approach is different from the Apache option. I don't just mean practically, but I mean ideologically. HiTran is centering the analog computer much more than the digital one. But that pushes us into an issue we've already discussed. Remember the whole matrix switching idea? How it reached a point where, to be practical, you needed an analog machine that's more complex than a contemporary digital machine? In this case, we don't even need to use math. HiTran uses a digital computer to make an analog machine more capable. That's basically making an analog computer that's more complex than a digital machine. And HiTran does a pretty extensive job of that. It documents your analog program for you. It tracks data coming in over the analog-digital linkage. So, while HiTran still focuses on the analog machine, it does give you all the tools you need to create a truly hybrid program. But, back to the point, this puts us in a weird situation. We're using a digital computer to supplement an analog machine. We know by now that approach is a dead end. We can see that digital machines fully take over and analog dies out. Hybrid is kinda a blip that also fades away. What confuses me here, what fascinates me, is the why. Was HiTran viewed as some blip? Was it viewed as overcomplicating an analog computer as I've supposed, or was it seen as a viable path? I can't answer that question directly. What I can say is that HiTran continued forward. This is where we get to those complications I mentioned. In the years following the 64 paper, HiTran expands. Part of that expansion is the HiTran Operations Interpreter, or HOI. This is the real twist, I think. For this, I'm just going to read from my current companion for the month, Hybrid Computation by Becky and Karplus. Quote, "The online interactive language was created to minimize the bookkeeping chores associated with the preparation, setup, control, monitoring, checking, execution, and documentation of the analog program. HOI has benefited from the design and the reported experience of earlier systems, such as JOS and Fortran." End quote. A bit dense, I'll give you that, but informative. As the 60s continued, HiTran expanded to have an interactive interface. That interface used the same syntax as earlier versions of HiTran. It talked over the analog-digital link, and it was inspired by Fortran, boring, and JOS, interesting. Why do I say JOS is the interesting part? Well, you have listened to my rambling episode on Lunar Lander and Focal, right? No? Really? Let me give you the short version. Focal is a language that is kind of disturbingly similar to BASIC. It's used from an interactive prompt and designed for simplicity. Focal itself is a simplified version of JOSS, JOSS, which is also an interactive and time-shared programming environment. Catch the drift? HOI was similar to the old familiar BASIC prompt, but it was meant to handle analog computation. That instantly has some huge implications. As far as developer experience, this is great. It gives you back some of the interactivity that analog machines were known for. You can send in volts and get readouts from a terminal. This also strengthens that concept of digital computer as a supervisor to an analog computer. HOI lets you monitor and control an analog computer from the comfort of a digital terminal. Good or bad? Who's to say? But this is setting HiTran up as a pretty specialized tool on a pretty definite path. But this doesn't mean that HiTran dies out. Far from it. One thing that keeps shocking me is how late analog and hybrid machines appear. To close out, we're going to highlight a 1975 paper called Program Generation System for Modern Hybrid Computers, written by another EAI employee. 1975. That's so late. That's after we have microcomputers. Now, this paper is of particular note because it's describing an automation system for true hybrid programming. I think it really clears some things up. First of all, it puts HiTran into a better perspective. In this automated system, HiTran is used as a single component. It's used specifically for initial simulation, testing, setup, and then the linkage to the analog machine. Digital programming is handled by Fortran. There's also an interesting pre-processing step where a program decides which code needs to be done in the analog and which in digital. Let me restate that. HiTran is used as a single tool in a larger chain. If you work in the biz, that should sound pretty modern. These days, just about every project is automated with a large set of tools. That includes compilers, linters, static analysis tooling, testing frameworks, debuggers, and, well, one very relevant trick. Have you ever heard of infrastructure as code? If not, let me wax a little bit. We programmers have pretty good tools for tracking software. The key thing here is that we track software as text files. We write code as text and we can follow all the changes in that text. That lets us keep a good handle on the development process. On the other side of the house, we have deployment. That is, how your software gets out into the wide world. In practice, that's kind of turned into how your software gets up and running on a server. That step includes everything from what software the server needs to already be running, how your software is installed, how much memory that server has, and even where things are hooked into a network. Back in the day, that deployment process would be documented. You would have a file somewhere that explained what the software needed and how it needed to be deployed. This was usually a step-by-step list. It was all manual, all done by humans with keyboards. But times changed. At some point, I think in the mid-2010s, a better solution rose to prominence. That solution is called infrastructure as code. The idea is instead of writing documentation that a human follows, you have a program that can do deployment for you. Then you write instructions for that program, either in the form of a procedure or as a configuration file. This is really handy since it lets programmers treat deployment the same as the rest of their software. It's another piece of the larger toolchain. Plus, these procedures for deployment are written as text. They can be versioned and tracked alongside the software they deploy. It's a really slick setup to work with. The tool chain described by EAI is using HyTran at certain points in a similar way to infrastructure as code tools. At least, it reads that way to me. A HyTran program is compiled into instructions for how to deploy an analog patch panel. There is the missing step of automation there, but the intent feels very similar to modern infrastructure as code tools. Apache, for that matter, also has this aspect. At the end of the process, you get instructions for how to set up an analog computer. Again, the automation step is missing just because auto-patching was never really practical. But the intent is there. These tools exist to simplify the setup of analog computers. One part of that is how you put a program onto a patch panel. In other words, how you deploy a program. Just happens that it uses a bunch of cables instead of bits. Alright, that's finally the end of my electronic analog rabbit hole, at least for now. There is so much more to electronic analog computers than I first assumed. Really, this is yet another lesson for myself on why I shouldn't make assumptions. Electronic analog computers form their own heritage of machines, with their own advantages and their own challenges. As digital machines improve, we get these hybrids that seek to get the best of both worlds. But analog machines eventually reach their limits, while digital machines continue to improve to this very day. It's during that final period that we get hybrid programming languages. And they aren't at all what I expected. Tools like Apache and HyTran are programming languages that are written and compiled on a digital computer, but target an analog machine. Basically, they're cross-compilers. This flips things around. Now the digital computer is making up for the deficiencies of the analog machine. Specifically, the digital side is used to make the analog side easier to use. It's all about developer experience. And while neat, this does lead to a bit of a dead end. As I said, digital computers continue to improve. Analog, however, reaches a pretty hard limit. These days, analog devices still exist, but they're relegated to even more special purpose applications. But for a few glorious, magical years, we had hybrid computers. Thanks for listening to Advent of Computing. You can find links to Patreon, to merch, to everything over at adventofcomputing.com. I'll see you in 2 weeks with the next episode, and as always, have a great rest of your day.